Today I am here to discuss module 6 of unit 4, that is alternating current electricity. So, before going ahead, I must tell you that what we have done in previous module: AC circuit, components, reactance and mathematical expressions for pure R, L and C. And today in this module we will cover LR circuit, CR circuit, LC circuit, LCR circuit or RLC circuit. At the same time we will discuss impedance, LC oscillations, resonance, quality factor and applications of these circuits. Let us start. As we know, the fundamental circuit elements are the resistor, capacitor and inductor. These circuits elements can be combined to form a electrical circuit in 4 distinct ways, as RC circuit, the RL circuit, the LC circuit and the RLC circuit, with the abbreviation indicating which components they are used. In practice, however, capacitor are usually preferred to inductors since they can be more easily manufactured, both RC and RL circuit, from a single pole filter. It depending on whether the reactive element C or L in series with the load or parallel with the load. Frequently RL circuit are used for DC power and it is also used to RF amplifier, where the inductor is used to pass DC bias current and block the RF back into the power supply. Now, here we will start with circuit containing inductance and resistance in series. A resistor inductor circuit, that is RL circuit or RL filter or RL network, is an electric circuit composed of resistors and inductors driven by a voltage or current source. A first order RL circuit is composed of one resistor and one inductor and is the simplest type of RL circuit. A first order of RL circuit is one of the simplest electronic filters. It consists of a resistor and an inductor in series driven by a voltage source. Look at here in this figure, pure inductor of inductance L connected in series with a resistor of resistance R through a sinusoidal voltage source V is equal to V naught sin omega t plus phi. An alternating current flowing in the circuit gives rise the voltage drop VR across the resistor and the voltage drop VL across the coil. The voltage drop VR across R would be in phase with the current, but voltage drop across the indicator will lead to current by a phase difference of pi by 2. Now, voltage drop across the resistor R is VR is equal to IR and across the inductor VL is equal to I omega L, where I is the value of current in the circuit at a given instant of time. So, here voltage phasor diagram for LR circuit is as shown here. In the figure we have taken current as a reference quantity because same amount of current flows throughout both the component. Thus, from the phasor diagram we can calculate V as is equal to under root VR square plus VL square, that is equal to I under root R square plus omega square L square, and that is equal to IZ, where Z is equal to R square plus omega square L square raised to power 1 by 2. It is also known as impedance of the circuit, and the current in steady state is I is equal to V naught sin omega t minus phi divided by Z, and it lags behind applied voltage by an angle phi such that tan phi is equal to omega L divided by R. So, here we can show it using a demo or animation how this RL circuit works. Here we will show how alternating current varies across resistance and inductor when both are in series combination. So, if we saw this diagram, through this diagram we have the variation of L and R. So, we can see the frequency and voltage how it is changing across the graph. Suppose we have the value of L is changing, through this button we will see. So, you will look at this. So, this value is, as we are increasing this value, how the graph is looks like, At the same time, if I will change R, so you can see how the value of R changing the frequency. So, at a different voltage we can check it. Suppose we have a voltage of 1 volt, peak volt. So, we have the frequency is like this. So, same time we can see the inductance how it is changing, right. Similarly, by changing L and R, we can see this resonant circuit how it works and how the behavior of voltage is changing. So, from the above animation, we have seen how that current and voltage are showing the phase difference. Now, here we will discuss circuit containing capacitance and resistance in series. A resistor capacitor circuit, RC circuit, or RC filter circuit or RC network is an electric circuit composed of resistors and capacitor driven by a voltage or current source. A first order RC circuit is composed of one resistor and one capacitor and is the simplest type of RC circuit. That is, RC circuit can be used to filter a signal by blocking certain frequencies and passing others. The two most common RC filters are the high pass filters and low pass filters. The figure here shows that a circuit containing capacitor and resistor connected in series through a sinusoidal voltage source of voltage V is equal to V naught sin omega t plus phi. So, this circuit is showing how AC source is connected with R and C in series. So, here we can look at again the phasor diagram how this current varies through this circuit. Here we will see how alternating current varies across R and C when R resistance and circuit in parallel. We have given two button here in this file. If we change the value of R, so you can see this phasor diagram how it is changing, or this vector representation is showing how the values of I and V is changing. You can see here, suppose I will change here C, the value of capacitance. So, how the vector or the value of voltage and current varies. So, this way we can show how the voltage varies and current changing across R and C when both are in series. So, this is the phase difference between voltage and current here, which is of pi by 2. In this case, the potential difference across is V R is equal to I R, and across the capacitor V C is equal to 1 upon omega C into I. In this case, V R is in phase with current I and V C lags behind I by a phase difference of 90 degree. From phasor diagram, the resultant of V R and V C, which is the applied voltage, thus V is equal to under root of V square R plus V square of C, that is equal to I under root of R square plus 1 upon omega square C square, that is again equal to I Z, where Z is equal to R square plus 1 upon omega square C square. Here Z is called impedance of the circuit. Again, from the phasor diagram, applied voltage lags behind the current by a phase difference of phi, which can be written as tan phi is equal to V C upon V R, which is equal to 1 upon omega C R. Here Z is impedance. Now, we have discussed here again the LC circuit in this way. An LC circuit also called as resonant circuit or tank circuit. It is an electric circuit consisting of an inductor and capacitor connected together. The circuit can act as an electrical resonator, an electrical analog of tuning fork, that is, it also behaves like storing energy oscillating at the circuit resonant frequency. LC circuit are used either for generating signals at a particular frequency or picking out a signal at a particular frequency from a more complex signal. They are key component in many electronic devices, like we can use it in radio equipment. It is also used in circuit as oscillators, filters, tuners and frequency mixers. An LC circuit is an idealized model since it assumes that there is no dissipation of energy due to resistance. The purpose of an AC circuit is usually to oscillate with minimal damping if we are using LC circuit. So, the resistance is made as low as possible. The two element of LC circuit described above is the simplest type of LC network. It is also referred as a second order LC circuit. Such LC network with more than two reactants may have more than one resonant frequency. So, look at this diagram, what we observe. See, here we have inductor and a capacitor. So, what is happening here? You look at this. The charge flows back and forth between the plates of the capacitor. Through the inductor, the energy oscillates back and forth between the capacitor and inductor until if internal resistance makes the oscillation die out or vanishes. In most applications, the tuned circuit which applies alternating current to it, driving continuous oscillations. The tuned circuit's action, known as a harmonic oscillator, is similar to a pendulum swinging back and forth. The natural frequency, that is the frequency at which it will oscillate when isolated from any other system as described above, is determined by the capacitance and inductance. In tuned circuit electronic equipment, the oscillations are very fast, that is thousands to billion of times per second. Now, here we will discuss about the resonance effect. Resonance occurs when an LC circuit is driven from an external source at an angular frequency omega naught, at which the inductive and capacitive reactance are equal in magnitude. The frequency at which this equally holds is called resonant frequency. The resonant frequency of LC circuit is omega naught is equal to 1 upon under root LC, where L is inductance measured in henries and C is the capacitance measured in farad. The angular frequency omega naught measured in radian per second and frequency also measured in hertz, and it is expressed as f naught is equal to omega naught divided by 2 pi, or that is equal to 1 upon 2 pi under root LC. LC circuit are often used as filter, that is the L by C ratio is one of the factor that determines the Q factor, that is quality factor, and so selectivity. For a series resonant circuit with a given resistance, the higher is the inductance and the lower is the capacitance. So, here we can talk about also what are the applications of LC circuit. As the resonance effect of the LC circuit has many important applications in a signal processing and communication system, a series of resonant circuit providing voltage magnification. The most common application of tank circuit is tuning radio transmitters and receivers. For example, if we have to tune a radio to a particular station, the LC circuit are set at resonance for the particular carrier frequency. LC circuit also behaves as electronic resonators, which are a key component in many applications like amplifiers, oscillators, filters, tuners and graphic tablets and many more. Now, here we will discuss about LCR series circuit. A LCR or RLC circuit is an electrical circuit consisting of a resistor, an inductor and capacitor connected in series. The name of the circuit is derived from the letters that R is used to denote constituent component of the circuit. Or RLC circuit have many applications as oscillator circuit, radio receivers and television sets use them for tuning to select a narrow frequency range from radio waves. In this role, LCR circuit is referred as a tuned circuit. Now, here you look at this picture is showing a capacitance, inductor and a resistance and is connected to a source V is equal to V naught sin omega t, and these components are in series. Here we have L, C and R in series, and we can see how these three when connected in series, the voltage, current across the resistance, inductance and this register how it varies. So, this phasor diagram is showing like this. Again we have 3 button. If we change the value of R, we can see how the current and voltage is behaving. Both are directly proportional. This green graph is showing like that. Suppose we change the value of L or inductance, how it changing. So, you can see through the graph this way. So, if I will decrease it, how the frequency is increasing, and same suppose I change the capacitance, you can see it here, and the behavior of the current or voltage you can see through this phasor diagram. Here you can look at this. So, here the values are changing when the value of R and C is changing simultaneously. If we took a one value is constant, how C is changing in the graph, and if I increase the L, how it is changing in this vector phasor diagram. The same amount of current will flow in all three circuit component, and vector sum of potential drop across each component would be equal to the applied voltage. If I be the amount of current in the circuit at any time, and VL, VC and V are the potential drop across L, C and R respectively, then VR is equal to IR, which is voltage in phase with I. Then VL is equal to I omega L, which is equal to that voltage is leading I by 90 degree. Here VC is equal to I divided by omega C, that is voltage is lagging behind I by 90 degree. Since VL is ahead of I by 90 degree and VC is behind by 90 degree, so that the phase difference between VL and VC is out of phase, or we can say 180 degree, and they are in direct opposition to each other as the phasor diagram shows. In this figure, it is assumed that VL is greater than VC, which makes I lags behind V. If VC is greater than VL, then I leads V. In this phasor diagram, OA represent VR and AD represent VC, then AC represent VL. So, as in this case, we can have assumed that VL is greater than VC, their resultant will be VL minus VC, that is represented by the vector AD. So, resultant of vector VR and VL minus VC is the resultant of all three, which is equal to applied voltage V. Thus, V is equal to under root VR square plus VL minus VC whole square, which is equal to I under root R square plus XL minus XC whole square, that is equal to I under root R square plus omega L minus 1 upon omega C whole square, where Z is equal to R square plus omega L minus 1 upon omega C whole square. Here Z is again same as impedance of the circuit. From the phasor diagram, current I lag behind resultant voltage V by an phase angle given as tan phi is equal to VL minus VC upon VR or XL minus XC upon R, or which can be written as omega L minus 1 upon omega C divided by R. From the equation we have three cases. We can say number 1, when omega L is greater than 1 upon omega C, then tan phi is positive, that is voltage leads the current. If omega L is less than 1 upon omega C, then tan phi is negative, that is phi negative means voltage lags behind the current I. And similarly, if when we take omega L is equal to 1 upon omega C, then tan phi is 0, that is phi is 0 and the voltage and current are in the same phase. Again considering if omega L is equal to 1 upon omega C, then we can have Z is equal to under root R square plus omega L minus 1 upon omega C whole square is equal to R. Thus, which is the minimum value of Z can have? This is the case where XL is equal to XC. The circuit is said to be electronic resonance. Hence, at resonance, omega L is equal to 1 upon omega C or omega is equal to 1 upon under root LC. Therefore, the frequency is equal to 1 upon f 2 pi under root LC. This frequency is called resonance frequency. Now, here look at the shape of resonance at the different value of R. So, as we see the graph, as the lower value of R, the peak value is maximum. At the same, if we decrease the R, so we can say that resonance is taking place or the sharpness of resonance is taking place.
Now, here we are showing how resonant frequency look like the graph or the pattern of the AC we can see here. We have this resonant frequency given by a formula which is written here, and if we change the values of L and C, so we can see the value of different frequency at different L. At the same time, if I will change C, how this frequency is decreasing this way, you can see. Same if we varies this R, so we can see how the amplitude of this frequency or this graph is getting down. So, at different voltage we can set a different type of voltage and inductance, where we can see the pattern of this resonant frequency. So, when the sharpness will increase, when it will decrease, we can see by changing the value of C and L at different period of time.
For small value of R, the resonance is sharp, which means that if applied frequency is lesser to the resonant frequency F naught, the current is high. Otherwise, for large values of R, the curve is broadside, which means that those is limited change in current for resonance and non-resonance conditions. So, what we have covered today in this module is LR circuit, CR circuit, LC circuit, LCR circuit, impedance, LC oscillation, resonance, quality factor, and we have discussed so many applications of these circuits. After finishing this module 6, we will study in next module how we comprises the power in AC circuit, wattless current and many more. Till then, goodbye.